Hi Lily again. Right, so you feel like you're testing me here. This is definitely not further maths. This must be rates of change in differentiation. And so you've got a log and it's a cylinder of radius 10 and height 25. I thought of a way to do this. It might not be the way your teacher wants, but it's one option. You can ignore the 25 height because you want the cuboid to be 25. So really all we're interested in when we read the bottom, find the value of x for which the area of the rectangle is maximum. So we really can ignore the height of the thing. We just want to use as much of that circle as we can, which to me screams a square, but we've got to fully justify why we'd want a square. Right, so when you've got your rectangle, that will probably become a square, but anyway. Not very good at drawing. And there's the centre of our circle, which will be also the centre of the rectangle. Whoops. So out to the corners, like here, basically. I'm just drawing sort of that, and that. Right, I know they're calling this one 2x, and they're calling that one 2y, because they might be different lengths. Although I can't believe they will be. Right, so what we want to do, we know that the radius is 10, so that means that has to be 10, and that length's 10, and that length's 10. Obviously you'd have another 2x there, a 2y there, and that's 10. This angle I don't know, I'll call it theta. And then because this is on a straight line, this angle here must be 180 minus theta. Okay. Right. Area of that thing then. Well, the area would equal, we've got two of this triangle, which we call these, we've got two of these area 1s, and we've got two of these area 2s if they're any different. Yep. So we'll have two area 1s, so 2 times, how we find the area of a triangle, a half AB sine C. So a half times 10 times 10, and the angle in between those 10s is our theta. That's a half AB sine C. And then we've got area 2, so we've got two of these. Oh, that's area 1. Area 2, we've got two of those. That was in area 2. So we've got 2 times, and the area of those will be, again, a half times, it's still the radius, so it's still 10 times 10 times sine. But this time that angle there will be 180 minus theta. So you can neaten that up a little bit. (100) sine theta plus 100 sine 180 minus theta. Right, we want to find the maximum area of this rectangle. So to find maximum, we differentiate and set dA, in this case d theta, equal to 0, because we want to find the maximum. So let's do that then. So dA d theta would be 100 cos theta plus, right, 100 cos 180 minus theta. But you might know the rule when you're differentiating that, we also have to times by the differential of what we've got here, the differential of that bit there. So the differential of that bit is minus 1 because it's a minus theta, so we times by minus 1. So we're going to set this equal to 0. So I'll turn over now. I need more space. So I've got 0 equals 100 cos theta minus 100 cos of theta, sorry, 180 minus theta. Divide through by 100. Actually, just take that over there. Let's do that first. 100 cos 180 minus theta equals cos 100 cos theta. So we can divide through by 100. We inverse cos both sides, so we'll get, basically you get inverse cos both sides, you'll end up with 180 minus theta equals theta. Take the theta over there, so we've got 180 equals 2 thetas, so theta must be 90 when the area is maximum. So theta equals 90 if we want the max area. Because it says in this question we have to fully justify it. What you'll also have to do is to show that that's a maximum and not a minimum. So to do that, you should really work out d2y by dx squared. So d2y by dx squared, if we remember what dy dx was, basically this line here. So if I differentiate that again, I would get minus 100 sine theta. Differentiate because you get plus 100 sine 180 minus theta times the differential of that, so it's times a minus 1. Yeah, and so what will well, so to write that one again, should I? Equal, so I'll take them, right, both minus, aren't they? So I'll take the minus 100 out, and in the bracket I'd have sine theta plus sine 180 minus theta. Like that. So when theta equals 90, we want to show that this is going to be negative to mean that that 90 is a maximum. If d2y by dx squared is negative, we have a maximum. Let's have a look. So sine of 90, put your calculator, we put in all that, that's 1. So we've got our d2y by dx squared equal to minus 100, and in this bracket sine theta is 1 plus, right, sine of, because we're putting 90 in, sine of 180 minus 90 is 90 again, so that's another 1. So this works out at minus 200. So because it's less than 0, we have a maximum, not a minimum. So we have a maximum at theta equaling 90 degrees. Right, so we've got our maximum, 90 degrees. So basically what we've proved, that this thing must be actually a square. If that's theta's 90, then these others, bad diagrams, these will all have to be 90. Ooh, terrible. So if that's 2x, I don't care what they say, that's 2y. We've proved that that has to be, again, 2y, which is the same as 2x, 2x, 2x. So basically showing it's got to be a square to be the maximum cuboid. Right. What's the value of x? Well, the value of x, when theta equals 90, well, we've basically just got a right-angled triangle now, haven't we? I will do it on this slide before I move off it. Right, so if I choose one of these triangles, one of these area 1s or area 2, they're all the same triangle. They're all the triangle anyway, but let's just draw it out. Right, that's 90. These two here are radiuses, so they're 10 and 10. All we have to do, and we know this is the 2x, so a bit of Pythagoras, 2x will equal square the other two and add them, so square root of 100 plus 100, which is 200, and then divide it by 2, so popping that in your calculator. So what we're doing root 200 divide by 2, and what does it come out? And I hate this calculator I've got here. Okay, comes out at 2 root 5. So that one is our final answer. That's our final answer. That's my x. So I've found the value of x, for which the area of the rectangle, which is a square, is maximum, and I think we've fully justified it by showing d2y by dx squared was negative, so a max, and we justified to find the maximum you had to set dy dx equal to 0. Must say that somewhere, I think I put it on the other slide. And then this bit, find the volume of the largest cuboid that can be cut from the log. Oh, wow. Volume of a cuboid. That's pretty straightforward, isn't it? So it's the area times the height of the cuboid, which is just, let me get a different colour pen, that red one. Yeah. So volume, I think it's only worth a couple of marks, will equal the maximum area, this max area, times the height of the cuboid, which is 25 centimetres. So the maximum area, did we work out an area? Maybe I didn't. So the maximum area, right, I don't have to go on another slide, or have I got any more colours? Purple. Hope you can follow this mess. I just don't want, I haven't got any more things. So the area of this big thing, oh, we know it's 2x then. So we can just 2x times 2x, isn't it? And we know x. So the maximum area would be 2x times 2x times 25. X is this 2 root 5. So it's basically 2 times that. So it's 4 root 5 times 4 root 5 times 25. Let's put that in the machine. My machine is not so good. Oh, I hate this machine. Delete, delete. Stupid things. That's coming out at 2000. So that equals 2000 centimeters cubed. And there we have it then. Oh, I'm putting a line through it. I didn't want to put a line through it. Highlighter. Yes. Oh God, it's the rubber. What a prat. Technology. Now it's on that blooming highlighter and I want the pen. Get off. $2,000. Try putting that back again. And then let's try putting the highlighter on it. Aha. It's a bit big. So that's my answer for calculate the volume, largest volume of the cuboid. Lots of thinks about it. Anyway, I hope you understood that one. Bye, Lily.